Dear students, this lecture is for explaining the third part of the applications of Gauss' theorem, that is problems related to plane symmetry where we are making use of the rectangular coordinate system. In the earlier lectures we have considered in detail some other types of symmetry such as spherical symmetry and cylindrical symmetry. And here also, as usual, we have to start with the integral equation or integral form of Gauss' theorem, that is surface integral E dot ds is equal to 1 by epsilon 0 volume integral rho dv. In the previous lectures, we have considered separate lectures such as with the discussion on spherical symmetry problems and cylindrical symmetry related problems. And in this lecture, we are exclusively considering some cases with the plane symmetry. And the different problems that we are going to discuss here are the first one is a plane sheet of charge, that is a plane sheet of infinite extent, a positive or negative charged sheet. Then another example is that of a charged conducting slab, that is with a specific thickness, a conductor with a specific thickness, and as an application or an extension of this particular conducting slab, we will identify or find out the electric field near a conductor of any shape. Then as the last case, we will discuss the electric field inside and outside a parallel plate capacitor. Let us take the first example, that is a plane sheet of charge of infinite dimension with the charge density sigma using Gauss' theorem. And here this picture shows a small portion of the charged sheet and a Gaussian surface in the form of a pillbox. A pillboxed shaped Gaussian surface, cylindrical Gaussian surface is shown with two flat ends of area A, flat end of area A, and the electric field is perpendicular to the flat sheet. It is extended to both sides of the sheet. Then sigma is the charge density and n is the normal. Here ds is shown as a small integration element ds. The electric field direction and normal are in the same direction, or ds is n ds, or it is in the direction of the electric field. Let us expand the left hand side and right hand side of the integral equation, and the charge enclosed within the Gaussian surface is the charge associated with a small circular portion of the charge sheet inside the Gaussian surface only. So a small portion of the Gaussian surface is there inside. Small portion of the charged sheet is there inside the Gaussian surface. And the area of that section is again A. A is the area and sigma is the charge density. So the total charge inside this portion of the Gaussian surface, total charge inside the this portion inside the Gaussian surface is given by sigma into A. So volume integral rho dv is equal to sigma into A. And the left hand side, we can see that there is actually three portions for the three sections for the Gaussian surface, two flat surfaces with the area A and one curved surface. And here we can see that the value of E dot ds is applicable for the flat faces only, and for the curved face E and ds are perpendicular direction. E and ds are in perpendicular direction for the curved face. So E dot ds is applicable for the flat faces only. So if we consider this as S1 and the curved surface as S2 and the other flat surface as S3, the integral E dot ds S changes to S1 plus S2 plus S3. out of which we can see that the contribution due to S2 is equal to 0 because E and ds are in perpendicular direction for that phase, that curved phase. Now the area of S1 and S2, the area of S1 element, S1 section and S3 section are taken as A. Okay, so here surface integral E dot ds is equal to surface integral E into ds because for S1 and S3, E and ds are in the same direction. That is for S1 and S3, E and ds are in the same direction, and also E is constant. E is constant there. So we are taking E outside, E into S1, S2, integral S1, S2 ds, and that is nothing but 2 times A. So E into 2A, E into 2A is the expansion of the left hand side. Now substituting this, we will get it as E into 2A is equal to 1 by epsilon 0 into sigma into A. E into 2A is equal to 1 by epsilon 0 sigma A, so that E is equal to sigma divided by 2 epsilon 0 in the direction of n, and this is the expression for electric field near a sheet of charge, infinite sheet of charge. So here the sheet of charge means there is no thickness assigned to the charge, only a thin film is taken into consideration. So electric field near a thin film is equal to sigma by, thin film of charge is equal to sigma by 2 epsilon 0. Now as the second case, let us consider a flat sheet of charge. A flat sheet of charge with the surface charge density sigma. So when a charge is given to a flat surface conductor, a conductor like this, a sheet conductor like this, due to the property of the charge distribution, we can see that the given charge distributes over the surface. So the charge distribution there will be on both sides of the conductor. So here also we are interested in identifying the electric field outside, just outside, using the Gauss flux theorem. So a Gaussian surface is considered, similar to the previous case, that is a pillbox shaped Gaussian surface. And here we are drawing this with one flat face outside and the other flat face inside the conductor. Okay, so this figure shows a small portion of the Gaussian surface is outside, that is a small portion is inside and the other portion is outside. So this portion is outside and here this is inside. And for simplicity, we are able to draw this in this form. That is, this is the conductor, and here this shows this is the Gaussian pillbox, a cylindrical shaped Gaussian pillbox, and the area is taken as A, and here this is the electric field, both also in the same direction. And we can see that the difference between the previous case and this case is that inside there is no electric field, so E is equal to 0 inside, so that the contribution from S3 part, so this is the S3 part of the Gaussian surface, this is the S1 part, and this is the curved part, S2 part of the Gaussian surface. And here the contribution is only from the S1 part of the Gaussian surface. So let us expand the both sides of the expression. So volume integral rho dV means the total charge inside the Gaussian surface, and here also a small surface charge region is there within the Gaussian surface, that is of area A, with the charge density sigma. A small portion is inside, so we are able to write it as volume integral rho dV is equal to sigma into A. That much portion of that small circular portion of the charge is inside the Gaussian surface, so it is equal to sigma into A. So coming to the left hand side, the expansion is surface integral E dot ds, that is S1, S2 and S3, 3 parts are there, and we can see that only we need to consider S1 of E dot ds, and here E and ds in the same direction, so E dot ds becomes E ds, and E is constant, so we are taking E outside, so surface integral ds means simply E into A, only one flat face is there. So Substituting this, we get E into A is equal to 1 by epsilon 0 sigma into A, and finally E is equal to sigma by epsilon 0 in the normal direction. So E is equal to sigma by epsilon 0 is the expression for electric field near a conducting slab, charged conducting slab. Okay, now this may be extended to find the field just outside the surface of a conductor of any arbitrary shape. A conductor of any arbitrary shape with a charge density sigma on the surface. So this is the example of the charged conductor, and a plus charge is given to this. Let sigma be the charge density. Here also we draw a pillbox to Gaussian shape, Gaussian surface like this, with a small portion of the Gaussian surface outside and a small portion inside. This portion is outside and here a small portion inside, and there is a small portion on the surface also. And we can see that there is charge distribution here on the surface. We can identify some charges present. So let us expand the integral equation. The right hand side, the volume integral rho dV is nothing but sigma into A, because here also we need to consider the electric field in the outside. Now electric field inside, since it is a conductor, E inside is equal to 0. So the left hand side, so only the charge is on the surface, so rho dV is equal to sigma E into A, and the left hand side expansion of the surface integral, we have to consider only the outer flat region as in the previous case. So E into ds, we will get it as E into ds, or it is equal to E into A. Though substituting the values, again we get E into A is equal to 1 by epsilon 0 sigma into A, or it is nothing but sigma by epsilon 0. So the result is the same. That is, for a conducting thick slab shaped conductor or conductor of any arbitrary shape, the electric field just outside that conductor is given by sigma divided by epsilon 0. Now, as the last example, let us consider the case of a capacitor. So in this case, we are considering a parallel plate capacitor. That is, two thin sheets of charge are assumed to be placed side by side. That is, on one sheet there is a negative charge, and the other sheet there is a positive charge distribution. So we want to find the electric field inside the distribution or inside the arrangement of the two plane sheets, and also the electric field outside the parallel plate capacitor. So initially, let us start with the electric field near a charged sheet. The expression for electric field near a charged sheet is given by E is equal to sigma divided by 2 epsilon 0. And let us place one more charged sheet. That is, some minus sigma is given to the first first sheet. Then a plus sigma is induced on the other sheet. In the case of capacitor, that is the situation. And initially, suppose we consider there is only one charge sheet present. That is, some minus sigma charge sheet is only there. And we can see that the electric field due to that minus sigma on both sides will be coming towards, and this arrow mark shows that the electric field on the right side, it is coming directed towards the charged sheet. Similarly, here also it is towards the charge, and it is represented on both regions. Here we have divided the capacitor region into three regions: the region 1, region 2, and region 3, where region 2 is between the two sheets 1 and 3 and outside, 1 at the left side and the other 3 at the right side. So in presence of minus sigma only, we can see that there is electric field distribution with magnitude E towards the sheet of charge with the magnitude sigma by 2 epsilon 0, sigma by 2 epsilon 0. Now suppose instead minus sigma, suppose the plus sigma charge only is there, this plus sigma only is present, then it will produce the electric field moving away like this on both sides. Now if both the electric fields, so both the charges are placed simultaneously, that is plus sigma and minus sigma, we can see that the electric field produced by minus sigma and plus sigma add up vectorially. That is, for the region like this. See, for the region, so if you consider the region for the first region, this is the first region, and for the first region we can see that the electric field, let it be E1, that is the first region, electric field is E1, and E1 is given by sigma by epsilon 0 minus sigma by epsilon 0, that is one due to the plus charge and the other due to the minus charge. Both are equal in magnitude, but they are in opposite direction, so that the electric field in the first region is equal to 0. Then for the second region, that's E2, the second region, we can see that the electric field due to the negative charge and electric field due to the positive charge, both are in the same direction, so they add up. E sigma divided by 2 epsilon 0 plus sigma by 2 epsilon 0, and the electric field is given by sigma by epsilon 0, sigma by epsilon 0, electric field inside. And for the third region, E3 similar to E1, we can see that sigma by epsilon 0 minus sigma by epsilon 0, because electric fields due to plus and minus charges are in opposite direction. So sigma by 2 epsilon 0 minus sigma by 2 epsilon 0, and the result is electric field is equal to 0. So it is a very easy method for finding the electric field inside a parallel plate capacitor. Now, so we have discussed some problems related to plane symmetry, and by making use of the integral equation of Gauss' flux theorem, we observed that within one or two steps we are able to find out the electric field very easily. So cases with such plane symmetry situations, and also in the previous lectures we have considered spherical symmetry and cylindrical symmetry cases. In all these cases, we want to identify some regions where the electric field is constant. In the case of spherical symmetry, we are able to find out a sphere over which the electric field is constant, just like the case of a point charge or in the case of a spherical dielectric charge. And with radius r, we have constructed a spherical Gaussian surface, and the electric field is found to be constant there. And similarly, in the case of a cylindrical symmetry, a line charge, etc., there also we find out we were able to identify a region, a curved region, a cylindrical surface over which the electric field is constant. And here, for the plane symmetry, we are able to identify a plane region over which the electric field is constant. So in such situations or in such electrostatic problems where some symmetry is available, then the use of Gauss' flux theorem makes the solution very easy, and instead of using the Gauss'S Law or other methods, it is very easy to follow the use of Gauss' flux theorem in such situations. That is all about this lecture. Okay, thank you.